We will now look at the second problem for this lecture, shortest superstring. Assume you're given some alphabet. For example, our alphabet that consists of the letter A, B, C, and so on. And you also have a set of strings over this alphabet. What we want to do is we want to find a shortest superstring. That means we want to find a shortest string that contains all these given strings as a substring. For example, I can give you 3 strings CBAA, ABC, and BCB. What is the shortest string that contains all of these? An easy way to get any superstring is just take all these strings and put them next to each other. So we start with CBAA, ABC, BCB. But it is easy to see that this is not the shortest string, because we are using 3 A's here, but if I just remove one of those A's, then it still contains all the strings. We still have CBAA, we still have ABC, and we still have BCB. Also, we have BC here and BC here, so we can remove a B and a C, and we again have a shorter string. This still contains CBAA, ABC, and BCB. So we have one string with 7 characters. Is this the best one? There's actually an even better one. We can start with ABC, then add BCB with just one additional letter, and then add CBAA. So we get a string ABCBAA. This only has 6 characters and it contains all these strings as a substring. And this is the shortest superstring for this set of strings. If we want to solve this problem, we can have an assumption, that is, that no string is a substring of any other string. Because if that's the case, then we don't even have to look at Si. As long as our superstring contains Sj, it also contains Si. So this is an assumption we can do without loss of generality. This doesn't change the problem instance, it doesn't change the solution. But why did I choose to include this problem into the lecture? The reason is that there is a nice connection to set cover, and that we want to explore in the following. We can model this shortest superstring problem as a set cover problem. Remember, for a set cover instance, we need a ground set U, we need a family of sets S, and we need some cost function C. So if we have some shortest superstring instance, and we want to model it as a set cover instance, what do we have to use to build these 3 things? First, we want to figure out what is our ground set. The ground set is just the strings that we are given, and we somehow want to cover all these strings. But with what do we want to cover them? That's our set family. And to define that, we have to be a bit creative. We will define strings. A string sigma I, j, k has these 3 indices. The first index I stands for a string Si, the second for a string Sj, and k stands for a number of characters that they overlap in. So we can build a string sigma ijk, where we first have the string Si, at the end have Sj, and the overlap is exactly k characters. And for that, for every pair of these strings, we can define some of these superstrings. These are just 2-element superstrings. For example, if Si is CABAB and Sj is ABABC, what superstrings do we get? We can overlap them with 2 characters AB. Then we get the superstring CABABABC. Since the overlap is 2, this is the string sigma ij2. But we can also overlap them with 4 characters, and that gives us a superstring sigma ij4. And from these 2-element superstrings, we want to define our set family. So we compute all these sigma ijk's that are valid and put them into our set family. What we still need is we have to define what strings are covered by these superstrings. This is quite easy. If you give me one of those, then we just take all the strings of our input of our ground set that are a substring of the sigma ijk. So S contains all the elements of the ground sets that are covered by sigma ijk. Since we want to find a superstring that's very short, we somehow have to measure the length of the string. So we just set the cost of one set that corresponds to some sigma ijk to the number of characters in sigma ijk. And this gives us a complete set cover instance. So our goal is, if you give me some instance of shortest superstring, I create this set cover instance, I try to solve it, probably with a greedy algorithm that we had before, since we know this is the best thing we can do. And from the solution that we get for the set cover instance, we want to read off again a solution for our shortest superstring instance. The problem is that the set cover instance that we are building might not give us the optimum solution for shortest superstring. So it can be that we create the set cover instance, we approximate it with factor log k, and then we get a solution for shortest superstring, and that solution again is by some factor worse than the optimum. So the approximation factor that we get can be some factor times the approximation factor of set cover. And in the last part we want to analyze this and try to find out what the factor of an approximation algorithm is that we get by reduction to set cover.